Hey everybody, and welcome back to Patel Academy. Today I wanted to go over the 2019 AP Statistics Free Response questions to give you guys an idea on some of the major types of concepts and ideas that might come up on the upcoming AP Stats exam, as well as talk about some of the major errors, as well as my explanations for some of the questions, so that you guys know exactly how to formulate your answers to your questions on your exam and are guaranteed to ace it or get a 5. Now, one of the things I will say is that this will model a timed walkthrough, so I'll be closely following the timing guideline to the best of my ability. But if I go a little bit above and past it, it's because I'm trying to explain some of the concepts or some of the alternate methods for some of the questions. Now, for a lot of these questions, there might be alternate ways, but some of the important ones that I feel you guys should recognize, I'll specify. And I'll also try and specify some of the calculator syntax that you can write down for common questions, like questions involving the normal distribution. Alright. So just before I get started, I wanted to start off with a very important phrase. Context is key. So for all of these questions, especially on your exam, be sure to read the scenario very carefully and interpret all your answers in terms of the numbers and in terms of the context given in the question itself. Because oftentimes there are marks associated, or there are levels associated with you interpreting it in terms of the context. So just a quick recap in case if you don't know the marking scheme yet. They do it based off an EPI format. And so essentially they have a list of components for the different parts of the question, and you have to meet all of them to get an E, parts of them to get a P, or none of them to get an I. And so a lot of times even the smallest of things are counted in components. So for this exam, being very precise and clear is essential. Alright, so let's get started with question number 1. So it says that the sizes in square feet of 20 rooms in a student residence hall at a certain university are summarized in the following histogram. And part A says, based on the histogram, write a few sentences describing the distribution of the room size in the residence hall. Okay, so whenever we analyze a histogram, it's important to consider 3 main characteristics: center, spread, and shape. So I'll talk about shape first. As you might know, shape literally means the shape of the graph. And so in this case, I see 2 peaks within the graph with a valley in between, or a low point in between, and 2 maxima. And so that represents a bimodal shape. So it is a bimodal distribution. Now, whenever we have a bimodal distribution, it's a subset of a cluster distribution. And so what we can say is that most of the room sizes fall within 2 clusters. So we have 2 clusters. It's important to specify these clusters, so I'll say it's between 100 to 200 feet squared as one of them, and then the other one is 250 to 350. Alright, that's for the most part the shape. There's not too much else that we can talk about, so let's move on to center. Center generally means mean or median. Now, you usually represent median here, and in this case, because it's unclear, if we didn't have part B, which I'll talk about in a second, you would generally give a range. So I'd say, okay, the center is probably between 200 and 300. So I'd give that interval. However, because we're given part B, what you are actually allowed to use is directly say, as long as you specify the exact number, we can directly say the mean is equal to 231.4 and the median is 253.5. So while you are allowed to do that, just to be safe, know that the interval method will work in case if you aren't given this information. Now, while we do know that there's a lot of measures of central tendency, we don't need to list each and every one of them. So just the mean and the median are enough. We don't have to talk about quartiles or anything like that yet. So that was center, and then in terms of spread, we kind of already talked about it a little bit with shape, talking about there's two main clusters, but we can talk about the range of the distribution. That's something we haven't done yet. So the range, now because you could again use the table and say, okay, it's the maximum minus the minimum, so it's about 171. But if you wanted to do an interval, you could say, well, okay, this first and last block within the histogram, so it's the first one is from 100 to 150, the last one is 300 to 350. So the minimum range is going to be the innermost bounds, so from 150 to 300, i.e. a range of 150, or the outermost bounds, from 100 to 350, we can have up to 250 feet squared as a range. Except now we're given the exact value as well if you look ahead as 171. Now I did do bullet points because writing it out would take much longer for me than you would on pen and paper, but these are the main things. And then just a quick thing to indicate, no apparent outliers. So that could go under spread, or I just wrote it as its own little separate thing, but there are no apparent outliers. And this will come into play maybe a little later. Hint, hint. Okay, so that was question 1A. Now we're moving on to question 1B, where we're given our table for the summary statistics, and it says determine whether there are potential outliers in the data. Then use the following grid to sketch a box plot of room size. Okay, 1B, we're trying to find outliers. To find whether there are outliers, there's essentially two different methods. So I'll cover both of them for completion's sake. So the first method is you use the interquartile range and the outermost quartiles. So outliers, they are data points that are less than Q1 minus 1.5 times the interquartile range, or greater than Q3 plus 1.5 times the interquartile range. So that is the first method that you can use. And so when we calculate our interquartile range, we just take Q3 minus Q1, and so we get 118 feet squared. And so Q1 minus 118 is equal to minus 1.5 times 118. And Q3 plus 1.5 times 118 is equal to 469. And so there are no values outside these bounds. And thus no outliers. Okay, so that was the first way that you can do it. And that's using the quartiles and the interquartile range. The second way that you can do it, that isn't often taught, but it is helpful, is if you utilize the approximation with standard deviations. And so essentially what you can say is, I like to let my k value be equal to 3 just as a reference, but you can say that outliers have to stay outside of x plus or minus k standard deviations. And so I usually like to let k equal 3. And so then my boundary, if you take the mean minus 3 times the standard deviation, so 231.4 minus 3 times 68.12, I get 27.04. And then if I add, so 231.4 plus 3 times 68.12, I get 435.76. And so all the data points are also within this interval, and so we can see that there are no outliers. So just two helpful techniques for you to know regarding calculating outliers. The first one is the most common one, but the second one can be handy sometimes if you don't have the quartile data. Okay, so the second part of part B is to draw this box plot. Now, I don't have the exact diagram here, but I will try to approximate it to the best of my abilities. So remember that in a box plot, the box has one of its lengths is Q1, the other side is Q3. The length of the box is the IQR, and then the whiskers go to the min and the max, or technically Q0 and Q4, depending on if there are outliers. Because we don't have any outliers, it would go to the min and to the max. Okay, so let me try and draw a general box and whiskers plot first, and then I will just label the values accordingly. Oh, and then keep in mind that box and whiskers plot also has the median. Not the mean involved anywhere, but the median is present. So, median is approximately over here. It's a little bit shifted to the right compared to the center. And then, yeah, you just label. This definitely isn't the scale, but you'd say, okay, this is 292, this is 315, this is 253.5, this would be 174, and this would be 134. And so yeah, that would be, you would draw it on the grid, obviously, with a pretty to scale drawing, but those are the critical values that you would need to show in your box and whiskers plot. Okay, and then going back to white for part C, what characteristic of the shape of the distribution of room size is apparent from the histogram but not from the box plot? Well, if you remember all the things that we discussed in shape, it's the very first thing that we can't really see, that it's a bimodal distribution. You have no way of ascertaining that it is a bimodal distribution through the box plot. But the histogram tells you the general cluster distribution, and so you can see trends of shape like this. And so that's why this is an application of how a histogram might be more useful than a box and whiskers plot at some points. Okay, so that was question number 1. Now keep in mind, once again, I want to reiterate that I am not writing the full sentence answers, but when you are doing your exam, each of these things should be done in full sentence answers. So for example, for part C, I'd say the histogram clearly shows the presence of a bimodal distribution among the data of room sizes, something that cannot be discerned from the box plot. All right. 2A. So question 2 says, researchers are investigating the effectiveness of using a fungus to control the spread of an insect that destroys trees. The researchers will create 4 different concentrations, 0, 1.25, 2.5, and 3.75 milliliters per liter. An equal number of the insects will be placed into 20 individual containers. The group of insects in each container will be sprayed with one of the 4 mixtures, and the researchers will record the number of insects that are still alive in each container 1 week after spraying. Okay, so question 2A says, identify the treatments, experimental units, and response variable of the experiment. Okay, so here's where we get into experimental setup. This is another topic that's very commonly talked about within AP Statistics questions. And so it's fairly frequent. So you should definitely revise the terminology of what it means, otherwise you're not gonna know necessarily, you're not going to know necessarily what exactly the question is looking for, especially in a situation like this where they use very precise terminology. Okay, so the treatment in this case are going to be the sprays, with the different concentrations, and it's important to indicate that there are four: 0, 1.25, 2.5, 3.75. It's important to indicate that the levels of concentration are different and that there are four different treatments, and then to indicate what those treatments actually are. Now, I'm not sure if the units necessarily matter, but to be safe, I would include milliliters per liter as well. Okay, the experimental units. Now, this was one of the things that confused people, because you often don't see this term come up, even when you're talking about experiments, but the experimental units are not the insects. They're the containers that the insects reside in. So officially, the experimental units would be the containers containing the insects. So I'll write that down. So it would be containers with insects. So this interpretation is a little bit difficult, but you have to consider it in a literal sense. What you're doing is you're spraying a container with different amounts of fungus mixtures, right? So in the most literal sense, you are doing something to a container, and thus the container becomes the experimental unit, not the insects directly. So this was definitely a challenging question to interpret for quite a lot of people, because a lot of them said insect, but I believe you'd only get partial marks for that in later questions. So maybe for this particular question, you still get full marks, but for later questions, you might be doxed them because you used that. And then the response variable, which is what you're looking, is the number of insects alive 1 week after spraying. So that's given to you directly in the question. Response variable, number of insects alive in container 1 week after spraying. Okay, now one of the things that I always say to students is it's important to be specific wherever possible. So don't start writing like paragraphs upon paragraphs, but for example, in the response variable, I took directly what the question said, every part of it relevant to that. So for the treatment, I said the exact concentrations, I said exactly what the treatment was. So it's important to be specific where possible in order to ensure that you get the full marks. Okay. 2b. Does the experiment have a control group? Explain your answer. Well, it doesn't explicitly say that there is a control group, but indeed there is. Now, this was a fairly obvious question. If you caught it, we have a 0 milliliter per liter mixture. So we're doing nothing to those sets. And so, yes, there is a control group, because the container is sprayed with a 0 milliliter. So containers with the 0 milliliter per liter solution form the control group. Form the control group. That word does not look like control. Okay, that was part B. It was fairly easy. Also, I know this is a little bit counterintuitive to what I just said, but when it says explain your answer, it again doesn't necessarily mean you have to write a paragraph. So for this case, it was just a very simple sentence. Yes, there is, because containers with 0 milliliters per liter solution form the control group. I should probably say because 0 ml per liter contain no fungus. Yeah, so that would be a complete response. And then part C, describe how the treatments can be randomly assigned to the experimental units so that each treatment has the same number of units. Okay, this is where an RNG is the best and the easiest option to go with, a random number generator. So one of the key things that is important to think about is that when we're doing a random sample, so when we're doing random everyone should have equal probability. So one of the things that you can do, now keep in mind as well, where the experimental units in this case is containers. So what we should be doing is assigning containers a fungus concentration. So what we can do is we can say, okay, we can use a random number generator from 1 to 20 because we have 20 containers, right? And so with a random number generator, each number would have an equal probability as long as we say this is without replacement. So there is a chance that even with a random number generator with just the bounds 1 to 20, that if you didn't take out the number from the list, it could repeat. So that's generally what, so your usual computer-based random number generators or pseudo-random generators can still repeat values because if it's in such a small bound. So you have to specify without replacement. And then you can say the first 5 numbers can be our control. So the next 5 numbers is the 1.25, the next 5 numbers is the 2.5, and the last 5 numbers is the 3.75. So what this allows us to do is, I should probably say beforehand, each container is assigned a number from 1 to 20. That's the only reason why picking these numbers, the first 5, second 5, makes sense, because the numbers represents the containers. So you pick the first 5 containers into control, next 5 into the first experimental set, next 5 into the second experimental set, and the last 5 into the final experimental set. Some other solutions involve you drawing cards or using a 20-sided die, anything that can randomize the number, and then you just have to discard repetitions. And so that's essentially, I personally think that because of time limits, whenever you see random assignment, always go straight to RNG, a random number generator. It's the fastest way, and it's probably one of the easiest things to write an explanation for as well. So That's just my opinion, but if you guys prefer using die or things like that, then that's completely up to you. And it still would be correct as long as everybody would still have an equal probability of selection. Okay, so that was question number 2. So 1 and 2 were fairly straightforward. Now we start getting into slightly more challenging questions. So a little bit more calculator oriented. Not calculator necessarily, but calculation oriented. Okay, so it says a medical researcher surveyed a large group of men and women about whether they take medicine as prescribed. The responses were categorized as never, sometimes, or always, and the relative frequency of each category is shown in the table. One person from those surveyed will be selected at random. What is the probability that the person selected will be someone whose response is never and who is a woman? Okay, so for this first one, now I personally like writing it out sometimes with words, but definitely you can use the set notation, so union or intersection. So never and woman. How exactly would we solve this? Well, if we look, there's only one place where you can have never and woman because it's and so it's just 0.0636. So part I, very simple. Part 2, sorry, I'll make that more legible. Part 2 says, what is the probability that the person selected will be someone whose response is never or who is a woman? So the probability of never or a woman, if we use the formula, is the probability of never minus the probability of being a woman, plus, and then minus the probability of what we just found, never and woman. I believe these are given in the formula as well under the probability section. Let me just go check really quick. So yeah, P of A or B, so this is the set notation I was talking about, so the probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. And so what we find is we can just use the data given from the relative frequency to say, well, the probability of never is 0.12, the probability of woman is 0.53, and the probability of both is what we just found, 0.0636. And so our final answer would then be 0.5864. Okay, and then part 3 also looks like a probability question. What is the probability that the person selected will be someone whose response is never, given that the person is a woman? So now we get into conditional probability. The probability that it is never, given that the subject is a woman, is equal to the probability of never and woman divided by the probability of woman. So once again, I'll scroll up just so that you guys can see. This is given in the formula sheet. The probability of A given B is the probability of A and B divided by the probability of B. So we can use that information, the probability of never and woman, we calculated as 0.0636. The probability of woman is 0.53, and our final answer is 0.12. So here's some quick probability calculation questions. Now for 3B, it says, for the people surveyed, are the events of being a person whose response is never and being a woman independent? Justify your answer. Okay, so one of the things to think about in terms of independence, there's a couple of ways to go about it. One of them is significantly easier, though. If two if two events, let's say if A and B are independent, what we know is that the probability of A and B is the probability of A times the probability of B, if they're independent events. So this is probably the easiest way to go about proving something like this. But what you can also say then is that the probability of A given B is still going to be the probability of A and B, now divided by the probability of B. But then using what we just found, this will simplify to the probability of A. And so you can use that either. So both of these ways will work. So let's consider it now in terms of a problem. So the events of a person whose response is never and being a woman, are they independent? Well, the probability of never and a woman we found is 0.0636. If we multiply the probabilities, so if I multiply 0.53 times 0.12, I get 0.0636. So using this first fact, because the probability of never and woman is the probability of woman times the probability of never, say 1 and 2, so using 1, probability of woman times the probability of never is equal to 0.53 times 0.12, which is equal to 0.0636, which is equal to the probability of woman and never. I started using the set notation just to save space. But using 1, we prove that they are independent. And we could do the same thing with 2, or we can flip 2 to get probability of B given A, and then do the same thing, and we'd still get the same answer. Okay. So part C, assume that in a large population, the probability that a person will always take medicine as prescribed is 0.54. If 5 people are selected at random, what is the probability that at least 4 of the people selected will always take medicine as prescribed? Support your answer. Okay, so in things like this, well, you can probably pretty easily see that we're given a probability, we're given a bound, so at least 4, but up to 5. This is a binomial distribution that we're going to be using. And so I'll just give you an idea on the way that I like to present my answer for a binomial distribution. This is one of the ways that I think College Board does it as well. I'm not too sure though, but it's one of the most common ways that I've seen. And it's to have a random variable as your answer. And so what we would say is define X as the number of people who always take the medicines as prescribed. So define X as the number of people taking medicine as prescribed. This just helps with the presentation of the final answer, because now what this simplifies to is the probability that X is greater than or equal to 4. And so we know that this is a binomial distribution now, so we can use the formula for a binomial distribution. So I'm going to have 5 choose 4 times 0.54 to the power of 4, 0.46 to the power of 1, plus 5 choose 5, 0.54 to the power of 5, 0.486 to the power of 0. So plugging this in, I would get 0.19557 plus 0.04592 and this is equal to 0.24149. Alright, so that is the total probability. Now, one of the things that you probably should do, it is given in the question, but sometimes, especially if you're going to do calculator syntax, which I'll show right now, you should probably specify your parameters before you do a test or before you do a calculation. So I probably would have said with n is equal to 5 and p is equal to 0.54, this probability that x is greater than or equal to 4 is blank. If we were to do calculator notation though, which is probably what most people do, you would have to write it something like this. I'd say it's 1 minus my binom CDF, and here it's important that you specify the parameters. You don't just write them down. So I would say n is equal to 5, p is equal to 0.54, upper bound is equal to 3, because we're going from 4 to 5, so our upper bound is 3. So it's really important that you specify exactly what these numbers mean. If I just wrote binom CDF 5, 0.54, 3, I don't think you would get any marks. Maybe 1, but I don't think you'd get any marks for that. So it's important to realize that you're supposed to specify all of these things. Okay. So, question number 4 was interesting because it didn't have any parts to it. So it says, tumbleweed commonly found in the western United States is the dried structure of certain plants that are blown by the wind. Kochia, I think that's how you pronounce it, kochia, a type of plant that turns into tumbleweed at the end of the summer, is a problem for farmers because it takes nutrients away from soil that would otherwise go to more beneficial plants. Scientists are concerned that kochia plants are becoming resistant to the most commonly used herbicide, glyphosate. In 2014, 19.7% of 61 randomly selected kochia plants, the words randomly selected are important here, were resistant to glyphosate. In 2017, 38.5% of 52 randomly selected kochia plants were resistant to glyphosate. Does the data provide convincing statistical evidence at the level of alpha is equal to 0.05, so at the 95% confidence level, that there has been an increase in the proportion of all kochia plants that are resistant to glyphosate? Okay, so this is a very loaded question. There's a lot going on over here, so I will try and break it down to the best of my abilities. The first thing that I notice is that we're given percents. Okay, percents represents proportions. And so we're given two proportions from two random samples, and so what you immediately should think of is a z-test for a difference between two proportions. So what I would say is, first of all, I'd like to define my parameters. Whenever you do a test, a hypothesis test, because that's immediately what we should think of when we see the words provide convincing statistical evidence that there's been something, we have to immediately define our parameters as the very first thing. Okay, so what I would say, let P17 or let P2017, P representing the proportion, be the proportion of population of kochia plants that were resistant to glyphosate Western US, resistant to glyphosate in 2017. Okay, similarly, let P sub 2014 be prop of population It's the same thing, of kosher plants in western US resistant to glyphosate in 2014. This was the actual exam. I would write out the entire thing the second time, but I just want to save a little bit of time, so I'm not going to write out everything again. Okay, so now we've defined our two proportions. So what we should know now is that we're going to define our null hypothesis and our alternate hypothesis and our test. And then we're going to say why the conditions of the test, why they're satisfied. Then we're going to run our test, find our p-value at the level of alpha equals 0.05, and then we're going to interpret everything in context of the question. So there's about 3 main steps. I'll write them on this slide. I'll erase them afterwards. But for any hypothesis test, part 1, define parameters slash values, define parameters slash values and hypotheses and test to use. So that's part 1. Part 2 is define conditions of test and show that they are satisfied. And then part 3, run test, get p-value, interpret in context, and conclude in context. Alright, so those are essentially the major steps for any hypothesis test. Keep those in mind. I'm not sure exactly how AP marks it, but at least when I did my statistics stuff, I'm pretty sure the scoring guidelines had sections very similar to this. So there were points allotted for defining parameters and hypothesis. There were points for conditions of test, stating the test, and explaining the conditions or explaining the scenario. And then there were points for the calculation, for your p-value being accurate, and then for your interpretation. So it's very similar to these 3 sections or steps. So just keep that in mind. So moving back, we've defined our variables. Now what I'm going to define are my hypotheses. So we want to, our data, we're trying to see if it proves that there's been an increase in the proportion of kochia plants over time. And so our null hypothesis would then be that there's no increase. And no increase represents that P17 minus P14 is equal to 0. Now one of the things I will point out, just before I write my alternate hypothesis, is that my null hypothesis says that the 2 proportions are going to be equal, or the difference between the 2 proportions is going to be 0. What this allows us to do is use a pooled test statistic to get a more accurate result. So because it's equal to 0, our null hypothesis, we can use the pooled statistic. If it was equal to any constant, not 0, then the pooled statistic would turn out to be inaccurate. So just keep that in mind, because for this I will be using the pooled test statistic formula, not the regular test statistic formula. So that's our null, and then we have our alternate hypothesis. So we have P17 minus P14 has to be greater than 0 to show that there's an increase over time. Sorry, I changed my variable names. They should be P2017 and 2014. Let me see if I can fit that in. Okay, so P2017, P2014. So now that we've defined our null hypothesis and our alternate hypothesis, we can then say our test that we're going to do. So the appropriate inferencing test to utilize in this scenario is a two-sample z-test for a difference in proportions with a pooled Z test statistic given by, let's see if I can fit this in. Z is equal to P2017 minus P2014 divided by, oops, I might not be able to. Yeah, that's okay. I'll just go on to the next slide. So the appropriate test statistic is the pooled Z test statistic given by Z is equal to P hat 2017 minus P hat 2014 divided by the square root of PC 1 minus PC divided by N of 2017, which is the total number of samples in the 2017 population, plus the same P at C, which I probably had it, times 1 minus P at C divided by N of 2014. Okay, and so this is where P at C is N 2014 P 2014 plus N 2017 divided by N 2014 plus N 2017 is the pooled estimate. Pooled estimate proportion. Alright, so that was a lot for the setup, but with questions like this, the hypothesis tests are probably going to be your longest other than the investigative task, which is question number 6. So that marks the setup for it. These formulas are something that I personally memorized just so that I wouldn't have to keep flipping back and forth, but I'm not sure. I'll check right now actually to see if the pooled test statistic formula is given. No, I don't think so. Yeah, so for two sample, the difference of sample proportions, this formula is given, but not the pooled formula. So that would be something that you would have to memorize in order to use in this case. But I do believe that if you just did your unpooled, you would get a slightly inaccurate answer, but it shouldn't be significant enough to where it impacts your overall answer. You should still get the same final conclusion, and I believe they would accept it, if you didn't pool. Okay, so that was the setup. Now comes the conditions. So this was step 2 in that little guide that I did earlier. So these are the conditions. So what is the first condition? Well, conditions, they're gathered from independent random sampling. Or, as we often go as an alias, SRS. And then this would be for 2014 and 2017. Okay, so that's the first condition. The second condition is that we have a relatively or approximately normal sampling distribution. Okay, so that's condition number 2, and then condition number 3 is kind of related to condition number 1. It's sometimes stated explicitly. So independence. So oftentimes what we do is we say we test just for SRS and then we test for independence within the SRS. So I'll just put a star, say it's related to 1. Okay, and so that kind of also goes the test for independence and then the normal sampling distribution. Sometimes you would have to use the central limit theorem as well in terms of the sample, so that could be a fourth condition. It's not necessarily explicitly stated though for the test for difference between proportions, but oftentimes you want to check if n, your sample size, is greater than 30. In this case it is, so you could explicitly say that, but it shouldn't. I don't recall it being a condition for this particular test. Okay, so now that we've stated a condition, we have to state why it's true. So 1. Well, we are told the question indicates that we take a random sample. So that can be your proof that the question indicates a random sample of 61 was taken in 2014 and a random sample of 52 was taken in 2017. Okay. We can state as well, it is reasonable to assume that the selection of plants in 2017 is not connected to that of 2014. So that was for question number 1. So we kind of indicated the independence. because we're saying that the two samples are independent of each other. But the third part of the third condition regarding independence is within one sample, talking about independence because we're going to be selecting without replacement. Okay, for number 2, we're talking about the sampling distribution being approximately normal. Now, why is this satisfied in this case? Well, normally you could say that it's approximately normal based on the central limit theorem. But for this one, you have to take it a little bit further. You have to talk about expected values. You have to say that the expected values are all greater than 10. And so for the expected values, because we're using a pooled estimate, we first have to calculate our pooled estimate. So using this formula, the n 2014 times p 2014 plus n 2017 times p 2017 all over n 2014 plus n 2017, we get 0.2835. Okay, so our expected values. Now e at x generally represents the expected value of a random variable. But I'm just going to use it as being, so this is n at p and then n at 1 minus p for sample n. And so my expected values come out to be 17.29, 43.71, 14.74, and 37.26. And each of these are greater than 10. So that is essentially how we prove for sure that the second condition is met. Now for the third condition, talking about independence within a sample. We do this because we took a sample without replacement. Now it doesn't explicitly say that, but it is fairly obvious. You're not going to be selecting the same plant twice within a sample. Otherwise you wouldn't have 62 samples, you'd have 61 samples and one repeated twice. So in this particular case it doesn't make sense. We're not given any information on the population sizes, but we can assume that we have a large plant population size. So what we can do is we can say that the sample sizes are less than 10% of the full population size. So this is where there's some logical thinking involved in statistics. The population of a plant that's this common, like tumbleweed, most probably has a population size in the millions, at least in the tens of thousands or hundreds of thousands. And so it's very easy to assume that the samples are less than 10% of the population size, and thus we can prove independence within the random sample. And so now that we've done that, we move on to the last part, which is actually doing our test. And so our Z test statistic, when we plug in all the values, 5 minus 0.197 divided by square root 0.2835 times 0.7165 to 0.2835 times 0.7165 divided by 52, and I get 2.21. Okay, utilizing this, we can go to our z-score table. Were we provided one? Yeah. So we were provided a z-score table. Our z value is positive 2.21. Keep in mind we're running at alpha of 0.05, and we get our probability as being 0.9875, and thus our p-value is 0.013. 0.135 or 25. Oh, sorry, I'm looking in the wrong column. 2.2, this is the alpha is equal to 0.05. So it's 0.9878, so 0.13 approximately, yes. And if you did it directly in your calculator, you'd be able to get a similar p-value probability. So p is equal to 0.0135 off of a calculator, 0.0122, I believe, directly off the z-score table, or 0.013. So very similar. Now what we can do is we interpret this. So we have our p-value, and so we say, sorry, I'll scroll back up to the question. So because p is less than alpha is equal to 0.05, there is sufficient, or there is convincing, as the question says directly, there's convincing statistical evidence to conclude that the proportion of resistant plants in 2017 is greater than that in 2014. Plants in 2017 is larger than that of 2014. Okay, and so just going back one more time through this entire thing, we define our parameters, we define our hypothesis, we define our test and our test statistic. In this case, we chose the pooled estimate proportion. We define our conditions, we prove why our conditions are satisfied, we run the test, get our p-value, and we say our conclusion, that we either reject the null in favor of the alternate hypothesis, or we accept the null hypothesis. Or you can't accept the null, you don't have enough evidence to reject the null. And that marks question number 4. Now, just quickly, before I move on, I wanted to cover some of the alternate ways. I'm not going to go through them because that would take a lot of time. I'm already at the hour mark. But 2 of the different ways alternate ways. So one of them was to do a 2-sided confidence interval. And then through that, you could predict whether the values lied within the interval, and thus whether you could predict whether or not you were able to reject the null hypothesis based on that. The other way, one of the more common ways, confidence interval wasn't used that much, but you could have also used a chi-square test for homogeneity. And so what you would get was a two-sided or a two-tailed test. Now, I'll leave it an exercise to you guys to work through all of the steps for a chi-square test for homogeneity using the information. But what I will tell you, if you want to verify, is that you would get a chi-square statistic of 4.8821. This is with 1 degree of freedom as appropriate in this situation. I'll make the equal sign look better. So that, and then your p-value would equal 0.02714. But because this is a two-sided test, our actual p, which I'm going to denote by p prime, would become 0.01357. So we would still get the same answer. And so this was another method that students chose to use, and it's perfectly viable. Just want to outline them so that you guys know some of the different things that you can do, and you guys can work with whichever one you're most confident with. Personally, I am very confident with both chi-square and z-test, so I, in this case, chose to do the z-test first, but either is viable. Okay, question 5. So, a company that manufactures smartphones developed a new battery that has a longer lifespan than that of a traditional battery. From the date of purchase of a smartphone, the distribution of the lifespan of the new battery is approximately normal, with mean 30 months and standard deviation 8 months. For the price of $50, the company offers a 2-year warranty on the new battery for customers who purchase a smartphone. The warranty guarantees that smartphone will be replaced at no cost to the customer if the battery is no longer working within 24 months from the date of purchase. Okay, in how many months from the date of purchase is it expected that 25% of the batteries will no longer work? Justify your answer. Okay, so this one is a fairly simple probability question. All you have to do is use z-scores. So remember the formula for a z-score is x minus mu over sigma. So it's x minus 30 over 8. Now, we're at the 25th percentile because we're talking about 25%. And at 25%, this is one of the critical values that I recommend you guys know. It is of a standard normal distribution, at least. It is negative 0.6745. Okay, and so the 25th percentile, because over here we're calculating the 25th percentile, so the z-score at this point, the x value at this point that gives the z-score of negative 0.6745. So this is just some simple algebraic rearrangement. So we have x is equal to 30 plus 8 times negative 0.6745. So our value becomes 24.6 months. So that was just whether you knew or could find from a z-score table the critical value at the 25th percentile, and then utilize your formula for a z-score. So no probability yet. In part B now, it says, suppose one customer who purchases the warranty is selected at random, okay? What is the probability that the customer selected will require a replacement within 24 months from the date of purchase because the battery no longer works? Okay, so again, using our z-score, we get x minus mu over sigma. This time we're given a value 24 minus 30 over 8. So that is negative 0.75. So what we're trying to find is the probability that the lifespan is less than or equal to 24 months. So it's the probability that our value z is less than or equal to negative 0.75. And And so this is just a simple calculator question, or you can look at it with the z-score. You get 0.2266. This also makes sense because in part A we found out that 25 at 24.6 months the probability would be 0.25. So before that, at 24 months, it should be less than 0.25. So 0.2266 does make sense. Now if you wanted the calculator method of doing this, this would just be normal CDF. I would say 0 is the standard, but my upper would be 24 because we're trying to find less than or equal to 24. And then I'd say mu is equal to 30 and the standard deviation is equal to 8. For 5a, I forgot to do this. I'll quickly do the inverse norm as well for the calculator syntax. So it would be inverse norm, I'd say percentile, or equals 25%. Mu is equal to 30. Standard deviation sigma is equal to 8. So that's what I would do for that. For this last part, part C, it says the company has a gain of $50 for each customer who purchases a warranty but does not require a replacement. The company has a loss of $150 for each customer who purchases a warranty and does require a replacement. What is the expected value of the gain for the company for each warranty purchased? Now, one of the things that you could and probably should recognize is the wording. It says, what is the expected value of the gain? They've clearly specified gain as being positive and loss as being negative. So they wouldn't, now they did specify negative gain, but most of the time, if they explicitly say gain, your answer should turn out to be positive. So that's just that's just like a little way to check. It is possible that it's negative, but like 90% of the time, they would have said, what is the expected value of the loss? So while you should immediately change your answer if you did everything right and you get a negative value, just know that that is a way to check for most standardized tests, is the wording. The expected gain for the warranty So I'll write expected gain. Now the warranty is the smartphone will be replaced if the battery no longer works within 24 months from the date of purchase. So we're going to have a probability of greater than 24 months and a probability of less than or equal to 24 months. Now this is an interesting question because it involves the interpretation of the question and the interpretation of the probability relative to the question. So we have a gain of $50, but because it's expected value, we have to multiply by the probability that my life is greater than 24, my battery life, sorry. And then I need to add a loss of 150 times the probability that my life is less than 24. Right, so that would be the expected value. Those are the two scenarios. We already calculated the probability that the lifespan is less than 24 in part B. And so it's important to realize that the probability that life is greater than 24, this should be less than or equal to, sorry, is equal to just 1 minus the probability that life is less than or equal to 24. And so my expected value is 50 times the value that we calculated. So this first part, is going to be 1 minus the value that we calculated. So it's going to be 0.7734. And then minus 150 times the value we did calculate, which is 0.2266. And so in the end, we get 4.68. All right, and so that is question 5. And now we get to the long question, question 6. So it's supposed to be about 25 minutes long. Oftentimes people are very daunted by the investigative task, but sometimes it's a fairly straightforward question. So Emma is moving to a large city and is investigating typical monthly rents of available one-bedroom apartments. She obtained a random sample of rental prices for 50 one-bedroom apartments taken from a website where people voluntarily list available apartments. Describe the population for which it is appropriate for Emma to generalize the results from her sample. Okay, so it's important to know that she utilized random sampling. So because we have used random sampling, and because our n value is equal to 50, which is greater than 30, we can say that the sample can be generalized to the population of available one-bedroom apartment prices in the city that are held on this website. So this is one of the important things that you have to keep in mind. You have to interpret it based on where the sample is taken. So the population of prices of available one-bedroom apartments listed on the website but it's also important to consider that apartment prices can change because you're going to a large city. So this was another small interpretation at the time of sampling. So this is important, that because of how prices can fluctuate, the sample taken is not only population dependent, so based on the website, but it's also time dependent. And so it's important to consider both of these things. And so the random sampling allows us to make this generalization that is related to the population, but it has to be at that particular time. And the sample is large enough to where we can consider it so. Okay, part B. Emma wants to estimate the typical... we're given the distribution of 50 rental prices in the following histogram. Emma wants to estimate the typical rental price of a one-bedroom apartment. Based on the distribution shown, what is a disadvantage of using the mean rather than the median as an estimate of typical rental price? So what we see is, if I draw just really quick, connecting the tips, we see something like this. And so while this isn't your traditional graph of this type of thing, this is skewed right. This second peak should have a much more drastic drop afterwards and in between, but it is a bimodal skewed right. I'll redraw it actually. So it goes like this. So you can very clearly see a skew right because the tail is extending onto the right with very low frequency of very high values. Okay, so because it's skewed right, we see that the mean is influenced by the outliers with a very high price and would overestimate. So what we would say is that the sample mean, so because the sample mean is substantially larger than the typical rental prices, so because the sample mean overestimates actually the word average here is not proper not the proper terminology. It should be typical. Rental prices. The sample median wouldn't be affected by the skew and would be a more accurate measure. Sorry if I'm getting a little messy. Hopefully you guys can hear what I'm saying and interpret what I'm writing from that. Just want to finish in time. Okay, so basically that's just talking about skew and how median is better than mean for central tendency in all places where it's not an approximately normal distribution. Okay, part C says, instead of using the sample median as the point estimate, Emma wants to use an interval estimate. However, computing an interval estimate requires knowing the sample distribution of the sample median for samples of size 50. A lot of the use of the word sample. Emma has 1 point, her sample median, in that sampling distribution. Using information about rental prices that are available to her on the website, describe how someone could develop a theoretical sampling distribution of the sample median for samples of size 50. Well, for a distribution, I should probably use the same terminology that they use, so I apologize, but I'm going to use the word sample a ton of times. For a sampling distribution of the sample median, for samples of size 50, Emma can take every possible sample of 50 one-bedroom apartments bedroom apartments, and then she can calculate the median, and she can amalgamate the median and can amalgamate the medians into a sampling distribution. There are some very long answers. So basically you take every single possible sample of size 50, find the median, combine all of those medians, and you get a distribution of every single possible median from a sample of size 50 on the website. Oh yeah, I should probably say where it says Emma can take every possible sample of 50 one-bedroom apartments, I should specify from the website. Okay, now we move on to part D. So because Emma does not have the resources to develop the sampling distribution, she estimates the sampling distribution of the median using a process called bootstrapping. So within this process, a computer program takes a random sample with replacement of size 50, okay, calculates and records the median of the sample, and repeats to get 15,000. So these are all of the frequencies of the different medians. Okay, it's a lot of data to think about. A bootstrap distribution provides an approximation of the sampling distribution. A confidence interval for the median can be constructed using a percentage of the values in the middle of the bootstrap distribution. So this is where this is more of an investigative task, because as seen in many years, we're given some sort of a new idea or topic or a new concept we haven't learned, and the task will walk us through all the steps. And so just jumping ahead, immediately I read question F and I say use your values from part D and E to construct and interpret a confidence interval, which is exactly what we're talking about. So parts D, E, and F are all going to combine and lead us through the steps of creating a confidence interval for the bootstrap distribution. So let's work through it. So part D, D part 1 says use the frequency table to find the value of the 5th percentile. Okay, so the total sample is 15,000, right? So the 5th percentile at 0.05 times 15,000 gets me 750, right? So I need to be 750 past the minimum in order to reach the 5th percentile. So what this means is at least 750 values less than or equal to what's a value? What would we want to call this value? I don't know. What's a Greek letter that we don't normally use, or do we want to use? I'll call it Y. So Y at 0.05 is going to be the value of the 5th percentile, and we know that at least 750 values are less than or equal to this Y. And so what we do is we just accumulate frequencies, starting with the smallest sample median and going towards the largest until you reach 750 values. So I see 1, 13, 18, 56, 4, 56, 55, 3, 66. So I'm at 272 so far when my median is 2,495. Then I had 136, and immediately I had 1899, and I go way too far. And so I know that my value of Y sub 0.05 is equal to 2,500 dollars. I don't have space, so I have to put it at the end. Similarly, for part 2, we want to find it for the 95th percentile, so I go 0.95 times 15,000, and I get 14,250. So at least 14,250 values are less than or equal to, I'll use the same naming convention, Y at 0.95. And so solving for this value. Now the trick is to, you can go down the columns until you get to 14,250, or to save time, you can now start from the largest and count down until you get to 750, because if 14,250 values are less than or equal to at least, then you're going to have 750 on the other side. And so I'm just going to start from the other side. This isn't properly how you do it, but it's the way to save time. So 3 plus 2 plus 6 plus 1 plus 12 plus 65 plus 6 plus 93 gets me to 188, and then at 700 I go past my 750 mark. So it's at 29, this time I'll put the dollar in front, 29.50. Okay, almost done. So we're on part E. Find the percentage of bootstrap medians in the table that are equal to or between the values found in part D. Okay, so between the 5th and the 95th percentile, so let me just calculate 1 plus 13 plus 18 plus 56 plus 4 plus 56 plus 55 plus 3 plus 66 plus 136. So that is 408 values before I get to 2500, and then 6 plus 93 plus 65 plus 12 plus 1 plus 6 plus 2 plus 3 is 188. So 408 values before $2,500 and 188 values after $29.50. So because the table says equal to or between, I need to take only the values before and after, not including any frequency that is equivalent to that value. So the 1899 that have values of 2500, I have to disregard those, and the 700 that have values of 2950, I have to disregard those. So then total samples equal to or between the 5th and 95th percentile. So the total number would be 15,000 total samples minus 408 minus 188, which gets me 14,404. Because this is 596, so 404, yeah. And so my percent is going to be 14,404 divided by 15,000, and then obviously multiplied by 100. And so I get 96.03%. And so we calculate our percent, and so what we should say is that, now what's interesting is that what happened sometimes, I'm not sure why exactly, but what happens sometimes with this particular question F is it says use your values from parts D and E to construct and interpret a confidence interval for the median rental price. Now we calculated the percent in E for a reason, because that is the percent of our confidence interval. So that is the strength, you can say, of our confidence interval. But for some reason, people often said that, okay, we're gonna take the 5th percentile, 95th percentile, in between there has to be 90%. So it's gonna be a 90% confidence interval. But no, that's incorrect. So you have to say that an approximate 96%, an approximate 96% confident interval an approximate 96% confidence interval for the median rental price of one-bedroom apartments For the median rental price of 1-bedroom apartments listed on the website is, and then our bounds are going to be 2,500 as we calculated in D part I, and then 2,950. So we've now used part D and E, and so our interpretation of a confidence interval is we are 96% confident that the median rental price of all 1-bedroom apartments listed on the website is between these values. Oops. Okay, and so that is the answer. We used D for our bounds, we used E for our confidence. Now, like I said earlier, people did do a 90% direct interval. Not sure why. I think you'd only get partial marks for that. And you'd only get partial marks if you didn't calculate the full interval and if you just used the bounds of, like, if you just used the range. So if you chose your interval to be 2345 to 3062.5, you'd only get partial marks for that. So this is the complete way of doing this investigative task. This is an important thing to consider, is that every part, at least once you get this like paragraph blurb, every part will lead into the next, and it's all connected to something, so use all the different sections properly. Alright, so that marks the end of the AP Statistics exam for 2019. I'd just like to say thank you so much for watching. I really appreciate all your support with these videos. I'm trying to branch out and do a wide variety, so this would be my first statistics video. I'm planning on doing some biology videos, maybe some environmental science walkthroughs, and then, as I've said in my previous videos, after I finish my AP work, I'm going to try and do some linear algebra and calculus 3 videos, so stay tuned for that. Remember to like, comment, and subscribe. Leave any suggestions down below, and remember to subscribe and hit the notification bell so you see all my future videos. I hope you guys learned something from this. Thank you all so much, and I'll see you guys next time on Patel Academy.